All right, we are moving right along to our area of parallelograms. As we chatted about yesterday, our area of a rectangle, that area is base times height. It's the same exact thing for our parallelogram. And if we remember from Unit 6, a parallelogram, technically, right, is a family, so a rectangle is a member of that family. What I found online, just to kind of demo this idea, is a little visual. Let me pull it up real quick. Oh yeah, here we go. That I think is going to be really nice for us to see this. Super simple, super straightforward, but I think beneficial nonetheless. Right, so this is our figure, our parallelogram, and we can move, right, this this triangle on the side to our other side to form this lovely thing called a, well, rectangle. Just to demonstrate, again, we just still need our area and we need that height. That height in our figure goes from base to base, from one side to the other side, forming that right angle. So that's a little visual to help us see why we're using that formula. So our area of a parallelogram is still base times height. Again, base is just one of our sides, and the height is the length that's associated when we're going from that base to that opposite side, right? That base to base. Okay, cool. So let's go through a couple examples. We might see some rectangles in here and some more specific shapes of our parallelogram family. We're just going through our rectangle right now. So we are given a rectangle and we're asked to find our area and perimeter of this. We probably will feel pretty comfortable applying this formula in these ideas just because we went over it yesterday. So I'm going to put that right angle in our corner. We are given a length of 5 root 5. So I'm going to assign one of those sides in our rectangle as 5 root 5, and then the diagonal as a length of 20. Again, finding that perimeter or that distance around the outside, I know that I need to find my missing side of x. So I can apply Pythagorean theorem, right? There's no shortcut to this one, unfortunately, to solve for that missing measurement. I'll simplify. If you plugged that into your calculator, make sure that 5 root 5 is all in parentheses and squared. Move that 125 onto our other side. And then take the square root of that 275, which we get x is equal to, we could split that up to root 25 times root 11, which is going to be 5 root 11 when we simplify that radical. All right, so there's our missing length, missing measurement of 5 root 11 now. To find that perimeter, we just need to add up all of those 4 sides together. So perimeter is going to be 5 root 5 plus 5 root 11 plus another, right, 5 root 5 with that opposite side plus 5 root 11. The two radicals, or well, like radicals that we can combine are the root 5s and the root 11s. So 5 root 5 plus 5 root 5 is 10 root 5. And then we have a 5 root 11 plus 5 root 11 to create your 10 root 11. Right, so that's our perimeter of our figure in units. Oh, we're given specific units as inches. So we can define that as inches instead. And then to find that area, it's just going to be a little base times height or length times width, meaning 5 root 5 times 5 root 11. Multiply that out. 5 by 5 is 25. Root 5 times root 11 is root 55. If we could simplify that radical, we would simplify that root 55 further, but there's no perfect square that divides into it. So our area of that figure would be 25 root 55 inches squared. This definitely involves some simplifying of radicals, right? Combining those like radicals. So a good recap of what we need to do. All right, moving on, we're getting back into our just regular parallelogram. 2, I think, is pretty straightforward. We're given some side lengths and we're actually given the height of this figure. So we have our, when we're trying to find our area, we really just need our base and our height. Our base, right, is that length of 12, and then we're given that height of 14. So I assigned that 12 as the base because looking at that figure, I know the height of it, right? That 12, its opposite side is 12, and then we have that height associated with that right angle. So that's why I used that height of 14 and that base of 12. I could totally use that base of 16, right? Its opposite side is CD, but we're not given the height from that base of 16. So my area of this figure is 168 units squared. I don't have a line for perimeter, so we're just going to have to add that in. Perimeter is just the distance around the outside, so I'm going to add up all of those lengths together. So I have 16, I have 12, I have 16, and I have 12. And those all add to 56 units. All right, so that's that perimeter of the parallelogram ABCD. We're getting into some more right triangle stuff, guys, with our area and height of this parallelogram, right? We're trying to figure out that shaded portion on the inside of this thing. And lucky for us, we do have that height drawn. So I'm hoping that we can see this lovely right triangle that we have. And it's a special right triangle. It's really special at that 60-degree angle measure in that side. So yes, we are applying our lovely SRT pattern, x, x root 3, 2x. Across from that 60, I'm assigning that x root 3. Across from that 90, I'm assigning 2x. So within that, I can solve for x to be 10, which will help me find the height, right, of that parallelogram by just plugging in that 10 to x, so I get a height of 10 root 3. That area is base times height. The base that I'm using, again, is what my height is drawn to. And in a parallelogram, we know opposite sides are the same. So that base, that whole side of that parallelogram is 35. My height is what I found that is drawn to that base of 10 root 3. I multiply those values together and I get 350 root 3. Oh, I have units, centimeters squared. My height is a singular distance, so we just use singular units as centimeters. Okay, so for our last example, we are going to do some, oh, sorry for the crazy scrolling. We're going to do some trig within our parallelogram, so bringing back that SOHCAHTOA in our area unit. So when we're looking at this figure, this lovely parallelogram that we have, right, we're going to use all of our knowledge of parallelograms so far. We know opposite sides are congruent, so I can label those things, right? 1818, 1212 centimeters. I'm also just going to throw down my formula for the area of the parallelogram, which is base times height. Technically, we can again use any of these sides as a base, but I think we want to use the angle that's given to our advantage, right, of this 55-degree angle measure. So if we look at this upper angle and create our height going down, right, that's going to be probably the most beneficial right triangle for us to use, just because we have that 55-degree measure in there anyways. And then with that 55, it's kind of gross in that there's no special right triangle, there's no Pythag for us to solve. We're just given this 55-degree angle measure and then one of our sides and trying to find one of our other ones. So using this 55, let's assign our opposite, hypotenuse, and adjacent to figure out which trig function we should use. So we need to find the opposite, and we're given the hypotenuse. So let's use a little sign, which involves our opposite and hypotenuse, right? So ka, toa, right? Just a little throwback with Unit 9. So setting up our sine function, it'll be sine of 55 is equal to the opposite as x over our hypotenuse as 12. And then we cross multiply, and we get x is equal to exactly 12 times sine of 55. Okay, this means very little to me. Let's find an approximate value just so we have an idea of approximately what that looks like. So we're going to multiply 12 by our sine of 55, and we'll get 9.829824, right, et cetera, et cetera. When you're plugging this into that graphing calculator, make sure your degree is in mode. So you'll go to second, actually not even second. You'll just go to mode. I'm sorry, that was an eraser. You'll just go to mode and make sure degree is highlighted, because this will help us in the future. Okay, so now we have our height, right? That x value, that length going from base to base. So that's what we'll plug into the formula for our height. So we'll take this whole value, so keep that in your calculator, of that 9.829824, et cetera, et cetera, et cetera, right? And then multiply it by that base of 18. And again, rounding to like 4 decimal places gets you mostly where you need to go. But remember, with this, we want to be as exact as possible. So 176.94. Let's round to the nearest hundredth, even though the directions don't tell us what to round to at that very, very end portion. Okay, so those were a couple examples dealing with the area of a parallelogram. If we think back to our family, which we're going to actually incorporate tomorrow, this formula applies to, yes, our parallelogram, but also our rectangle, our square, our rhombus, but we'll have some more specific formulas for us to use. Go ahead and flip onto that next page and start working on a couple example problems. They're not a crazy amount. I think there's 3 examples, but I want you guys to feel comfortable with applying your SRT within this parallelogram to find your area and also trig functions. So go ahead and pause the video, and then when you're ready to check your answers, unpause it, and I'll quickly scroll through those answers. All right, good luck.